Okay, so when we do this second derivative right here, it's undefined at -4, so I need to put in a -5. I need to put in a -3. So when I put a -5 into here, I get -5 plus 4. That's -1 cubed. -1 cubed is negative. Negative divided by negative is positive. Put in a -3 here. I get a plus 4 is a positive. 1 cubed is positive. Divided into a negative would be negative. So where is this concave down? When the second derivative is negative, -4 to infinity. Now, you would actually need no calculus to do this problem. Another thing that I will continue to say many times over is the more you understand about these basic functions, the better and easier you can make life for yourself, okay? What does a graph of 1 over x look like? No. Like that? It's a hyperbola. Like that right there. When you put a -4 into this, you get -3 over 0. We just got done doing stuff before Christmas. What do you have when you have -3 over 0? A vertical asymptote. Remember that? We were doing the whole stuff with limits. At -4, so right away, the first thing I do, and again, this comes from years of doing these, but what I'm trying to get across to you is as soon as I saw this problem, the first thing that jumped to mind was not concave down, was not y double prime. It was, what does this function look like? What kind of function is this? That's what I thought of. And I thought, you know, this is like a 1 over x, just shifted to the left 4, right? The plus 4 is just a shift left. Okay, that's all it is. Because that's the inside of that function is down here with the x. So that's just a shift left 4. So that's just this graph. Now it's got a negative on it. So what's it do is it flips this up. So right away, just with shifts and everything else, I knew this was a -4 as vertical asymptote. And this is going to come up and do this. And this is going to come down and do this right here. And remember we talked about high powers dominator. We talked about x goes to infinity. We talked about horizontal asymptotes. So I know when I put a really big positive number into this, like 1 billion, I'm going to have -3 over 1 billion. What is that? 0, really small, but it's negative, right? It's really small, but negative. So that's how I know this is coming up towards 0 from underneath. And if I put a really big negative in here, I'm going to have -3 divided by a really big negative. That's going to be positive, but really small, close to 0. So I know this is coming down from here. So just look at that graph. Where's it concave down? -4 to infinity, right? I didn't need any calculus for that. I didn't need any calculus for that. If I just think about what we talked about, recognize that there's a vertical asymptote here, recognize that this is an infinity situation, like where we talked about limits before, and know what this graph looks like, I get that. But, you know, you say, yeah, boy, I would never remember that. Well, okay, now you got the chart. You got the chart stuff we learned. But I picked this one on purpose, kind of tricky because it's never 0, but we also got to think about undefined. Where's this undefined? Okay, so a lot of stuff that we've done so far this year, any one of those things could be brought into this problem to help you to get that answer. Okay, homework. 4.4, any questions on 4.4 parametric equations? Because we're moving on to section 3 today.
So, like, to tell the direction, you just tell where, like, the kid's getting bigger.
Yeah.
That's the direction that it's going.
On the graph you talk about?
Yeah.
So as you just trace, so if you've got this graph that goes like, you know, and one of the things I said you have to be able to do on this next quiz is you have to be able to graph on your calculator a parametric equation. You have to be able to label some points. So like, if I want you to label it t equals 1, I want you to label it t equals 2. Maybe I want you to put the ordered pair there as well. So you would plug those. You'd have to plug in a 1, plug in a 2, write your x and y coordinates, right? I might want you to do that. And also, a lot of times I say sketch the graph and mark the direction of travel. So you just trace. And so at t equals 1, it's here. Then it's at 2. Well, that's clearly going this direction. So put little arrows on it, you know, showing the direction that this thing is going like that. So that's what I mean by mark the direction. Okay, so you just trace.
On 20, part A,
Yeah.
it asks what time the air drag ball crosses the plate. So
Right.
do you plug in, like, you have to plug into the equations, don't you?
You get x of t. Yeah, the whole thing is plugging into the equation. And so you got x. The air drag ball is the one where x was, well, what do you mean the second equation? Yeah, well, they give you two sets of equations there. They're the same. It's just that they told you what k was there, right? The value k is 0.003, so they went ahead and put that in for you. So yeah, you're using the equation. It's 1,000 ln 0.4t, 0.45t plus 1, right? That's all over 3. And then your y equation is 7 minus 16t squared. Is that what you're talking about? Right. So on 20A, when does the air drag ball across the plate? What did we say we did for that?
So do you set the x equal to 60?
Wasn't 60 point?
Which is around, in the graph, it's just around 60.
Well, I know it's actually just a little past. Don't you remember we did that? We did that in class. If you go back to example 10, it's 60 feet 6 inches. Yeah, the home plate's 60 feet 6 inches. So you plug that right there. Not in for t, but yeah, so it'd be 60.5 equals. You just solve that. Yeah, just do a solve on the calculator. Yeah, so that whole problem is exactly the same as the problem we did in class. Right? It's just, okay, if I want to know where it crosses a plate, that means when x is 60.5, so I'm putting x here. If I want to know when it hits the ground, I put a 0 in for y, because that's the vertical distance. Right? If I want to know, is it a strike, I want to know how high it is. I want to know what y is at that time. So I take whatever time I found when I did part A, and I'll plug that into t. And that'll tell me how far it is, which of course we know is 60.5. We put it into this one for t, that tells me how high it is. And then, of course, don't forget your speed equation. That's x prime squared, y prime squared. So you have to do the derivative of this. But that's easy. I mean, if I was going to do that derivative, number one, you could put it in your calculator. But really, here's how I would write that. Here's how I would write that equation. If I was having to do a derivative on this one, I would write it like that. That 1,000 over 3 is just a number sitting out in front. So x prime is going to be 1,000 over 3, and then and it just hangs out there. What's derivative ln? It's 1 over 0.45t plus 1. But you can use your calculator, so let your calculator do the derivative. I don't care. Times the derivative inside would be 0.45, right? So I mean that would be your x prime. I don't know if you ever need that. Do you need that? Well, you need it for the speed equation, don't you? You need it for the speed equation. So that was all those same questions we did. That one we did together. We'll review that later in the week. Because our quiz is not going to be till Tuesday of next week. We've got section 3 to do, section 4. Right? To be honest, parametrics will be the easiest of the 3 things we do, I think. Because, it's pretty much, here's your equations. I want you to be able to graph it, be able to trace, be able to set them equal to something. You just solve them. I mean, there's not a whole lot of setup and stuff you have to do, unlike the ones we're going to be working on this week. So, okay, does that answer that pretty much, man? Okay, anything else? 9A. See this curve, we've got one. Which bullet points would you expect to be moved quick? Well, that's the thing we talked about where it's just between the ones that are farther apart. You just look at that picture. You know what I mean?
Oh, you're supposed to.
On page 242, it says figure 1.
Oh, I just grabbed it. I didn't see the figure.
Oh, and there
I
is.
didn't know which bullet points he was talking about.
Oh.
Yeah,
Each point is one.
That's where it's slower.
Right. Each point is like one time unit, 1 second or whatever. So the farther apart they are, the faster it's going. Right. That's what they're talking about. Okay. And then in B, when it says estimate the speed, I mean, just look at some section. Just it's pretty straight. Like if it's barely moving up and it's mostly moving horizontal, you can kind of estimate how far it is in 1 second. That's all that we're talking about there. All right. Well, let's get your notes out here and let's move along to section 4.3, and this is really a repeat of stuff we've done already. We haven't done it since chapter 2. Of course, you remember chapter 3 was just about derivatives. I mean, chapter 3 was basically the gateway test. I mean, that's about all chapter 3 was learning how to do more complex derivatives. Chapter 2 is really about chart and local max min and concavity, like that problem we opened up with today. That problem we opened up with was chapter 2 stuff. That's where we learned all about all these interrelationships and things we can use a derivative for. But then we didn't know how to do a lot of derivatives, so we spent time in chapter 3 learning how to do all these derivatives. And now we can go back and kind of revisit those things from chapter 2 and expand on them. So this is called optimization. Section 3 is called optimization. Now, it's finding max and min. Okay? Because in many, many cases, those are the optimum situations. If I'm stranded in the snow and I want to get to the gas station, the minimum amount of time would be optimum, so I don't freeze. Right? If I have a business and I want to know how many things that I should make to maximize my profit, then the maximum, that's the optimum. Right? You see what I mean? So many, many times, either a max or a min is the optimum situation. So we can use optimization. That gives us one word instead of having to say max or min. Right? So that's what we mean when we're talking about an optimization problem. Now, mostly we're going to be talking about global max min here. Right? Not local max min. Most of the time. So if the problem just says find the maximum of this function, we read into that it means global, right? What is the minimum cost? What is the maximum profit? Whatever. How many things should I make? What price should I set to get the max profit? That kind of thing. Those are the kind of problems we're going to be doing. Okay, now, the key to that is finding a function for the thing we're trying to maximize or minimize. Okay? But before we get into that, I've just thrown up an example of a function. Many times we're going to have endpoints in our problem. Most of the time we're talking about a function on a closed interval. Okay, so I've got an example of a function. Where is the maximum on this function up here? What's happening? That's too simple a question. Obviously, we don't see where the maximum is. What's happening at the maximum here? What's happening at the highest point here? And here we're talking output, right? We say max, we're talking the y number. The slope is 0. So one place to look for a maximum is when the slope is 0, right? What's happening at the minimum here? Slope's undefined. So you could have, and what was the name we had for those? I mentioned it earlier. Slope 0 or undefined. What's that called? Stationary point is slope 0. No? Flexion point is when the concavity change starts with a C. Critical point. Critical point is when the derivative is 0 or undefined. Okay, so we're going to look for critical points. We're going to look where the derivative is 0 or where it's undefined. Okay, and very, very important that we don't forget about undefined. Chapter 2, we did a lot of problems with nice polynomials, nice and smooth. We didn't worry about any sharp points, but now we're going to get into that where we have to, just like today, the concave, just like this one here. right? We're going to have to worry about situations where the derivative or the second derivative, whatever, mostly just derivative because we're doing max min here, is undefined. Okay? Now, I could change this function just a teeny bit. I could change this function just a little bit and make the endpoint be down here. Now where's the middle? At the endpoint, right? So do you remember in chapter 2 when we had our LOC, right? Remember our list of candidates? And we said, where do you look for a global max and min? We said you got to look where the derivative is 0. You got to look where the derivative is undefined, and you got to look at endpoints. Now, another way to say that is you got to look at critical points and endpoints, right? I mean, that's another way of saying it. Now, I usually think of it as 3 places because to me, critical points is 2 places. Now, some people say it's 4 places because you got a left endpoint and a right endpoint, you know, whatever. To me, it's 3 places I got to look. I got to look where the derivative is 0, I got to look where the derivative is undefined, and I got to look at the endpoints. Okay? Well, sometimes you don't have any endpoints. Like just a plain old parabola. Where's the global max and min? Well, there is no global max on a parabola, but there is a global min down at the vertex. Unless it's upside down, it'd be the reverse. So it's possible you don't have both a max and a min if you don't have any endpoints, right? Or maybe you just have one endpoint, right? Maybe it's like the square root function, which doesn't have a max or a min. But if you got the square root function, which has an endpoint at 0 and then goes to infinity, so maybe you have a left endpoint but not a right endpoint. Now, there wouldn't be any max or min on that. Now, if you look at section 4.3 in your book, down at the bottom of page 234, okay, so on 234, they've got some discussion about stationary points, critical points, you know, if the derivative is 0 or is undefined, that's a critical point. If it's just the derivative is 0, then it's a stationary point. So we already talked about that. And now at the bottom, it lists something called the extreme value theorem, which is something we're going to talk about more later in the chapter. But the extreme value theorem says if the function's continuous on a closed interval, so if it's continuous and you have a left and a right endpoint, so there's no gaps or breaks or holes or anything, if the function's continuous and it's got a left and a right endpoint, then there has to be a high point and a low point. There has to be a global max and a global min. That makes sense. If you start one place and end at another place, you had to have a highest spot, you had to have a lowest spot. Now, if you take the sine graph from wherever to wherever, is there one global max? Oh, come on now. I tricked you. Is there one global max on the sine graph from wherever to wherever? I mean, let's say from negative 8 pi to 8 pi. Is there one global max? What is it? There's one global max. It's 1. Its high point is 1. Now, it happens a bunch of times, but that's not what I said. Global max. When I say what is the global max, I'm talking about the y-value. There's one global max. 1. There's one high point. Okay? It's 1. Now, it hits that high point several times, but there's one max value, and there's one min value, negative, right? Okay? But so it could be at an endpoint. It could be at where the derivative is 0. It could be where the derivative is undefined. So those are the places we have to check. So none of that's new. Okay, we're going to be a little more technical with our language and all that stuff, but none of that is new. Okay, so here's what we're going to do first, right here. Okay, let's find the max. This is a continuous function. It's a polynomial, 4th degree, nice and smooth. Nothing weird going on. We're going to look at it from there to there. Okay, no calculator. Find it. Find the global max and min. We actually did this back in chapter 2. Okay. Do your list of candidates. Check where the derivative is 0. Check where the derivative is undefined. Check the endpoints. the derivative 0? 0 and 3 over 2, 1.5, 0 and 1.5. Are those both inside of our interval here? Are those both between -1 and 2? Right? If they weren't, we'd throw them out. Where's the derivative undefined? Never. That's going to happen a lot, but we need to discuss it. Okay? So what I would suggest, so a good problem, a well-done problem here would look something like this. So we do the derivative, okay? So simple derivative, 6x squared minus 4x cubed equals 0. Now, I'm going to be honest with you, that one like this is not going to be on our next quiz. One like this was on chapter 2 quiz, right? I mean, we already did a problem like this. We're going to be doing story problems, right? But this gets us into it. This gets us through the mechanics of doing it, right? So we do the derivative, which is that. We set it equal to 0. I factor out x squared. You might be saying, well, you can factor out a 2x squared. That's true, but I don't care about the 2. I'm just trying to find what x is. Okay, so it doesn't matter. That's fine. Factor out a 2. That's okay. There's a calculator problem. Then you would still be doing a lot of this work. You wouldn't do this. You could just type that in and solve, because we might get into some more complicated functions and just let you use your calculator on it. I'm trying to think on this quiz. We might just do calculator on this whole quiz. So you could... because I'm not quizzing you really here on your derivative knowledge on this, so you could just do a solve of it. Once you do the derivative, which you could use your calculator for if you had to, that'd be silly on one like that, then you just do a solve, whatever, we got to solve it. So I get x equals 0, x equals 3 halves. Those are my critical points. Now, I usually, what I would say is you should also then say never undefined, right? We need to do our list of candidates. You've got to show me in these problems that you're checking all 3 of these places. So we've just shown by our work that we're checking where f prime is 0. We've just shown by writing down that f prime is never undefined. And the last thing we have to check is, and then we got our endpoints, right? Yes.
How do you check undefined?
Well, what do you mean? How do you check any? What do you mean, how do you check undefined? Oh, here's f prime. Is it ever undefined? Means, where is undefined? What causes undefined? What are the most common things that cause undefined? 0 on the bottom. Negative inside the square root, maybe. Those would be the big ones, right? A log function is never negative. I mean, if you have a log function, it means your original function was probably a log function. And, so x couldn't be negative maybe anyway, whatever. So the big ones are 0 on the bottom, negative in the square root, that kind of thing. But undefined just means you plug in a number, you can't get a number out, right? So polynomials are never undefined. So now how do we check? So when we say check them, what do we mean by check them? Why do we plug them back into the original? Because we're trying to find the highest and lowest spot, right? I mean, this is where people get confused about number lines and stuff. And we're not trying to find when this function is increasing and decreasing. We're not looking for that kind of thing. This isn't chart stuff, number line stuff. Now, number lines could come in here. I'll tell you about that in a minute. But you could do a number line, but that's usually a local argument, right? That's for local max and mins. You want to see that the graph's going up, then down. Then it goes up and down again. Then it goes up and down again. And so we got local max and mins that we have to tell where they are. But we want to know where's the highest point. So the way you tell the highest point on this function is you plug these candidates back into the original function, right? That's what you've got to do. That's what a list of candidates is. So you take 0, plug it back into the original function, you get 1. You take 1.5. Now here's why I would probably make these calculator problems, right? Because now it gets kind of tricky without a calculator to plug these numbers in here. Okay, so we're going to get somebody grab your calculator and plug one, just put 1.5 into that. I'll put a -1 into here. We get -2 plus 1 is -1. -1 minus 1, that's -2. Put a 2 in here, that's 8 is 16. 16 minus 16, so that's just 1 again.
It's negative 0.68875.
When you put in 1.5? Okay, great. You don't agree? You look like you don't agree. 1 plus 2 times 1.5 squared minus 1.5 to the 4th. Should be plus. Okay, so it's 2.6875. Okay, so what do? Isn't that our max right there? Now, I think it's best to just circle actually the Y value because that's what we're usually asking for. What is the max value? And the min value is right there. So the min value looks like it's at the left edge, and the max value is kind of in between there at 1.5, right? So we got the minimum value and the max. That is the process of doing a global max min problem. So that should be mostly reviewed, right? We check our list of because this is what we did this chapter 2, right? Global max min. Where's the derivative 0? Where's the derivative undefined? Where are the endpoints? Because that's where the high and low points can be, right? That's where the high and low points can be. Okay, but that's not going to be the hardest part. That needs to be the easiest part of these problems. This process needs to be the easiest part. You get to use your calculator for most of it. You can use a calculator to do the derivative. You can use a calculator to solve where it equals 0. You're going to have to look at it and think about where it's undefined, but that's mostly when there's a 0 on the bottom or a negative in the square root. So a lot of times it's not undefined anywhere. So a lot of times that's not an issue, but you got to write it down on what you're thinking about it every single time. The endpoints are usually given to you, but in the story problems, we do have to sometimes think about them a little bit. We have to think a little bit about what the endpoints are, but then we plug those back into the original function. We see which one's biggest, which one's smallest, right? So that process needs to be the easiest part of this. The hardest part of it, there are going to be story problems. The hardest part is figuring out what the function is we're trying to find the max and min of. That's the hardest part. Chapter 2, I just gave it to you. It said find the max and min. Okay? Now, let's go through, let's do another one. Okay? Find the max and the min of this. Now, stop. Take the lesson that I gave you earlier here just for a second. Remember when I said, when I looked at that problem, I didn't think about concave up and concave down right away. The first thing I did is look at the function and get a picture in my head of what it is. And I know I'll probably let you use a calculator this anyway, but geez, why do you need it? What does this function look like? Huh? It could look like a W. Fourth degree could have as many as 3 humps, right? And where do the tails go? Don't they both go down? Because it's negative 3x to the 4th. There's no endpoints. You got a W, possibly a W. It could just be a U, but it could be a W kind of thing. Could be a flat spot in there. And the tails both go down. So what's that tell you right away about finding max and min? There's not going to be a min, right? It's going to go down forever, right? Because there's no endpoint to stop it. So it's just going to go down in infinity. So there's not going to be a min, but there's going to be a max, right? There's going to be a max. So it's going to change a little bit about what happens here, okay? All right, so go ahead. Go ahead and get started, though. So you start the same way, your list of candidates. The difference is there's just no endpoints to check. But it's not a bad idea when you get into these problems if you already have an idea of kind of what's going on. Now, could you just graph them? Since you have your calculator, couldn't you just go in and graph this function and kind of get an idea already where the max means? Sure. You can do that, but you're not going to get points for that. All your points come from showing your work, showing your steps, all that stuff. Go ahead and use your calculator. Solve if you need to. All right, what do you got? I'm sure you guys are writing like crazy. I'm wondering why you're writing so much. What happens right here? Is that where you start? Right? And then don't you have to solve that, right? Don't you have to use a calculator to solve that? Right? We have to use a calculator to solve that. We can't factor anything. There's no, you have to. Okay, where does it equal 0? Okay. Right? What about f prime undefined? Yeah. Right? Yeah. Because it's a polynomial. I mean, it's just a nice smooth thing. There's no sharp points. It's never undefined. Okay? So, what do we do with our list of candidates? We put that point into the original equation. And use your calculator. Now, you should put in more than that. Okay? Should put more decimals in than that. Okay? So what I would do, what was the original equation? It was x minus what? X cubed minus what? 3 What was that? See, to me, this is a great, list of candidates is a great time to use a vertical bar, right? Great time to use a vertical bar. Because I'm going to be plugging a bunch of different things into a function. If I'm using a calculator, I'll just type in my function, and then I'll go to my vertical bar, and then all I have to do is go up and grab that thing. Or I can just type it, but now I can just grab that like that, right? And then I can change that to x equals 1, and x equals 0, and x equals whatever I want, right? I can just keep plugging in this value into that original function. It's not a solve. This is a solve. When I'm setting it equal to 0, I'm solving. That's a solve. This is just plugging in those values for us. Okay? 0.263. Now, is that a max or a min? How do you know it's a max? Okay. So, here, this problem is a special situation. Why do we do a list of candidates when we're trying to find a max and a min? To compare them, right? That's why you do a list of candidates. These are the only places, when you're doing this problem right here, you're saying that these are the only places that a max or min can happen because of what we talked about back here. The only place your high and low points can be. The only way it can be a high point is if it goes up and comes back down, right? Or if it's at the end. Right? That's the only way you can have a high point. You can't have a high point if it doesn't go up and come back down or be at the end. It's got to. And the only way it can go up and come back down is if it goes up smoothly and comes back down smoothly, which means the derivative is 0, or it goes up and then sharply comes back down, and then it means the derivative is undefined, right? So the only way you can have a high point, same argument goes for low point, is if the derivative is 0 or the derivative is undefined or it's an endpoint. It's the only way. So if that's the only way you can have a high and a low point, then let's take all those points and let's compare them, right? And let's see which one has the highest y value. And the one that has the highest y value is max, and the one that has the lowest is a min, right? We compare them. So, when you get to a problem like this, how many possible high and low points do we have? 1. Isn't that a problem? Isn't that a problem for a list of candidates now? How do I forget the argument that we said a minute ago? How do I tell if that's a high or low point? I can't. I only got one of them. There's nothing to compare it to. I don't know if that's a high point or a low point. Okay? So, what do you do when you only have one candidate? You have to make some other argument other than the list of candidates. The list of candidates is not good enough here. Right? You have to say what you just said. Say it again. Why do we know that's a max?
Because the endpoints go in the same direction and they're going down.
So you either have to write out a paragraph here or a few sentences that says this function is a 4th degree polynomial with a negative leading coefficient, so therefore it has the tails going in opposite directions like so, and since there are no endpoints, it will go down to negative infinity, so there will be no minimum. So any candidate, any place where the derivative is 0, like 0.367, has to be the maximum. You've got to say that in a well-worded way, right? You can't just say, well, it's 4th degree, or it's got to be the max, because the tails go down. I mean, that's not going to be good enough, right? That's not going to be good. Okay? You're going to have to say it in a well-worded way about that function. Maybe a picture could be helpful, why that is the max. Or, when have we done that? Number line. This would be the one time it's okay to use a local argument in a global max-min problem. So I don't mind the couple sentences describing the situation in a well-worded way. I think that's fine. But what I would probably do, now you're still going to have to you're going to have to write some words. But I think if I only have one candidate, I'm going to do a number line. I'm going to use a local argument and then convert it to a global argument. So what I would do in this problem is I would put 0.367. I would do my f prime. And now remember, now we're plugging into f prime, not f, right? And I would take some number here, and I would take some number here, and I would plug those in. So now when we get a 0, you plug in a 0, what do you get? Which is positive. And you plug in a 1, you get 1 minus 3 is negative 2. Negative 2 minus 12 is negative 14. Okay? So what does that tell you? There's one key word you're missing. Otherwise, that's a perfect argument. Instead of up and down, let's say increasing, decreasing. To the left of 0.367, this graph is, but no, f prime is positive. F is, put one word in front of there, starts with an A. F is always increasing, right? Because this is the only critical point. So what you would say here, instead of our local argument, which just says, hey, before here it's increasing then decreasing. That's what we want to say, because this is the only candidate. So we know there's nothing else here. So you would say F is always increasing before 0.367 and always decreasing after. Therefore, 0.263 is a max value. So that's how you could use when you have a single candidate, and that only is going to happen when you don't have endpoints, right? Because if you had endpoints, you would have 3 candidates, right? If you have endpoints, you're always going to have at least 2 candidates. You have your left and your right, so that'll be good. But if you don't have endpoints, and you only get 1 critical point, single candidate, don't use a list of candidates, because a list of candidates is only good for comparing. And when you only have 1, you can't compare. So that's when you can do a local argument. Okay, let's put this, let's go to our notes then, and let's write this down. I'm not a huge believer in, following a recipe or whatever the case may be, a set of steps, but I think there are times where it can be helpful. So I will usually refer to these sets of steps when we do this. Okay? So when we're doing a max-min optimization problem, step 1 is we need to identify what we're trying to maximize or minimize. Now, in these problems that we just did, it was easy. They just gave us the function. They said, find the max-min of this function. What we're going to be doing is, find the max profit, find the minimum cost, find the minimum time. So the first thing you have to do is identify, what am I trying to maximize and minimize? Okay, so that's the first thing I'll ask you. So what are we doing here? Well, you'll say we're doing the max volume. We're trying to find the max volume. Oh, okay. So we've identified what it is we're trying to maximize. Okay, step 2. Write and label an equation of that quantity. So then what I will say to you, okay, if you're trying to find the max volume, then you need to write a volume equation. So you need a V equals. You're trying to find the max profit, you need to write an equation that's P equals. That's going to be your function. Instead of F of X equals, it's going to be P of X or V of X. You always start by writing down an equation for the thing you're trying to maximize or minimize. P equals, V equals, C equals if you're doing cost. Okay? Now that's sometimes called the primary equation. In our older books, it used to be called the objective function. It's the objective of the problem to find the max profit or whatever. And some books now call it the primary equation, the thing you're trying to maximize or minimize. Okay? Step 3. Get that equation in terms of 1 variable. So that's not a problem in our chapter 2 problems that we were just given f of x with x's in it, right? We just had 1 variable. But if we want to maximize the volume, if we're doing a box, the volume of a box is length times width times height. That's got 3 variables in it. L times W times H. We can't have that. We can't have 3 variables in the problem. We've got to have 1 variable in the problem. So there's got to be some additional information in the problem that will allow you to do that. Okay? So these steps are kind of new, right? These steps we didn't have to do before because we were just given the equation we were trying to maximize or minimize. All right? And so the other information that's in the problem are called constraints, or they're called your secondary equations. Okay? So the first 3 steps are new. Once we get through those, we're then to the place we were in the last 2 problems that we just did. See, so to me, the first 3 steps are where the difficulty lies in these story problems, is getting the thing set up. Because once we have it set up, what do? Well, yeah, that's it, find the golden maximum. But what? We find the critical points, right? We do the derivative, we set it equal to 0, we check to see is it ever undefined, right? I mean, so now step 4 here was basically our step 1 before, right? Step 1 was, okay, now we just do our thing, right? We go through these steps. We'll go ahead and write them down. So we find the critical points. Where's the derivative 0? Is the derivative ever undefined? Now, step 5, we need to identify any of our endpoints. So remember, there's 3 places we look, where the derivative is 0, where the derivative is undefined, or endpoints. Now, we have to identify endpoints because a lot of times it's not going to be given. I mean, the story problem, right? Well, think about that snowmobile, right? The snowmobile was stranded. I think our variable was R. R was how long he was going to walk on the road. Well, the gas station, remember, was 6 miles from his position, right? So if you remember that problem, he was stranded in the snow. Here was the gas station. He was down here. This whole distance here was 6. He was going to walk at some point. This was going to be R, right? And then this was 6 minus R. Well, endpoints are your littlest and biggest inputs, right? Right? The endpoints are your littlest x and your biggest x. Well, in this case, it's R, but you know what I mean? Well, what's the littlest R could be in that problem? 0, right? He might not walk on the road at all. He might go right there. So R could be 0. What's the biggest R could be in that problem? 6. See how? So you're going to have to look at the problem, and you may have to come up with the endpoints, right? You may have to come up with the endpoints yourself, okay, based on the information in the problem. So 0 and 6 would be your 2 endpoints. So you've got to identify the endpoint. So that's a little new, a little different than the basic math problem, because that just gives it to you, okay? Then use list of candidates or a number line or some justification to identify the max and min. Most of the time it's going to be list of candidates. But we just went through that example showing that if you only have one candidate, then a list of candidates is stupid. Yeah, that's a little strong. But you can't do a list of candidates because a list of candidates is to compare them to see which one's the biggest, which one's the smallest. If you only have one candidate, there's nothing to compare. So you have to, so then do a local argument like a number line or some justification, right? And then answer the question with appropriate units. If they want to know how far did he walk on the road, if they want to know how long did it take him to get there, if they want to know how many units you should make to get the max profit, if they want to know what price you should set to get the max profit, if they want to know what the max profit is, you know, whatever, you have to answer the question that's being asked. Okay? All right. So that's the steps. So if that's helpful to you to have that to look at, to go down through the steps, you know, then I think that's okay. But at some point, I mean, we get to the quiz, you're going to have to, you know, just know those steps and what to do. Okay? All right, so like I said, in this problem, the first 3 were all there. Number 5 we didn't have to do because the endpoints were just given to us, right? We just did the derivative, set equals 0. It all went pretty fast. We do our list of candidates, right? Then we answer the question, which was just find the max and min value. Okay, so let's do this problem right here. Let's do the box problem. This is a classic calculus problem. One of the first problems most people think of, to be honest, when they think of an example for elementary calculus. Here's going to be, I'm going to make it a little easier. Say we have a piece of paper here that's an 8 by 10 inch. I know it's 8.5 by 11, but let's say we got an 8 by 10 picture. Whatever, I don't know why we would do this to a picture, I don't know. But I got a piece of paper that's 8 by 10, okay? And I want to cut out of the corners 4 equal squares and do what? What will I do with that paper when I cut out those 4 squares? It's called the box problem. I'll fold up the edges and I'll make a box, right? I'll fold up the edges and I'll make an open face box. And so it would be something like, when I get done, something like that, right? The question is, what size squares should I cut out so that this box has the max volume? That's the question. What size squares should I cut out of here so that this box will have the max volume? Because if I cut little tiny boxes out, right? If I cut little tiny boxes out, what will the box look like? so it'll be not very tall, right? It won't be very tall. It'll be longer though. It'll have a bigger this way, but it won't be very tall, right? If I cut great big squares out, it'll be mostly tall. It'd be like this, right? You get the idea, okay? So it'd be most, if I cut great big squares out, then I'd have taller sides to put up, but then the base of it would be small. This will be the base of it once I cut those squares out, right? This will be the base of it. And then these pieces will get folded up, right? Make a box. So, step 1 was what? So what are we trying to maximize? Volume. Step 2, write an equation for that. V equals length times width times height. Step 3. Get that in terms of one variable. So the question is, how much should I cut out here? Right? So what can I label this? The sides of my square here. Label it X. You want to label it X?
S.
S for square. Right? X could be okay. Actually, there's one that's already in the problem I could use. There's one I already got. Isn't it H? It's H, isn't it? But I don't care. It doesn't matter. I mean, it doesn't matter. You said S, so we'll use S. Okay? Use S. And that would be the same for all of them, because they're all going to be the same size square. Okay? So, I'm going to have length times width times height, and the height is going to be S. Right? So what will be the length? What will be the red here? This would be the length, and this would be the width. So what will be the length? No?
Not quite.
10 minus 2x is going to be that length, right? So the length of this is going to be 10 minus 2s. And the width? 8 minus 2s. All right, now you could distribute that all out, FOIL out, use your calculators. I don't care. I think, and now this is now V of S. Now I don't care if you write V of S, but before I couldn't really write it as a function because I had length, width, height. I had 3 different variables. But now I've got it in terms of S, so I can write this V of S. Okay? All right, so just multiply that out. Just type it in. It should just do it. If you just type that in your calculator and enter, it should just do it. I don't know, but for some reason I like to see it written out. But what do you got?
It's going to be 4S times S minus 5 times S minus 4. That's it.
So okay, so here's not that this matters. You don't have to do this. You can just leave it. But if you want to, you can go to menu, you can go to algebra, you can go to expand, and then grab that, hit enter. Okay, what's it say?
4S cubed minus 36S squared plus 80S.
Plus
Yeah.
80s. Okay. Now I don't care if you do that, but that's expand. Okay. So if you ever wanted to do that, type expand. Do the expand. All right, and then what? That was step 3. Find the critical points. V prime, which would be 12s squared minus 72s plus 80 equals 0. Now we could factor out some things, but who cares? You got calculators for this. Let's solve that. What do you get? You should already have, well, I guess, it's good to let the calculator do the derivative for you there, because then you just have it, and then when you do your solve, you can just go up and graph it, right? So that's one reason to let the calculator do the derivative for you, but whatever. 4, okay, and then that's it? 0.45. 0.45?
4.528.
All right, that's it, those two? Okay, all right. So is V prime undefined? No, it's just a polynomial, so V prime's never undefined. And then what was the next step? What was step 6? Is it step 6 or 5? 6? 5, I don't care, it doesn't matter. Step 5. Endpoints. 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 So now, when you're doing endpoints, what variable are you looking at? S. S, it's the input, right? It's the input. When you go back to here, what are these values right here? Those are X values. They're X values. They're the littlest X and the biggest X, right? That's what endpoints are. So the endpoints here are the littlest S and the biggest S. So look at your picture. What's the littlest S could be? 0. Wouldn't even have a box. If you don't cut out any corners, you're not going to have any volume. So clearly that's not going to be a maximum, but that's fine. Let's use it as an endpoint. What's the biggest S could be? 4. A lot of times people say 8. But no, the biggest S could be, if you use S as 4, then that's going to use up this whole side, right? You can't go any bigger than that. So the biggest S can be is 4. Now what's that tell me? I can take out the 4.528 as a candidate, because it's not going to be possible. Okay? If we try it in there, we'll probably get a negative volume, right? Which would clearly not be good. Okay? And so the next step is the list of candidates. Okay, we've got candidates, so we're going to do V of 0, we're going to do V of 4, and we're going to do V of 1.472, of course being very careful not to round that and not just plug in 4.72, but plug in a few more decimal places than that, and we're going to plug that into our volume. And so if you've got your volume typed in there already, that makes it nice, and then you can just grab that, do the vertical bar. It's not a solve. You're plugging values into it. I'll save you a little trouble. 0 and 4 are both going to give you 0. Right? You put a 4 into there right there. That one's going to be 0. So that factor is going to be 0. So you're going to get 0. And so what do you get? You get a number there. 52. Get that? 52.514. And then I don't know if we had inches on this or something, that'd be inches cubed. Okay, so that'd be your max, right? And it might be a good idea in these storage problems, instead of in your list of candidates, to actually write, so it might ask several questions. It might say, what's the max volume? So that'd be 52.514 cubic inches. It might say, what are the dimensions of the box? Well, then you got to come back here and say, okay, that's S. So that'd be the height. And then this is your length and this is your width, right? So if you want the dimensions of the box, it'd be 1.472 times, and you have to put 1.472 into this. To get the length, you have to put 1.472 into this to get the width, right? You have your length and width and height. So they might want the dimensions of the box that give the largest volume. But you have to have this, though, as your justification, and then the last part is answer the question. Okay? So that is what a optimization problem looks like. Okay? Real quickly here. One last one. We'll get it set up, and then I'll just I'll give you the homework and let you start working here. We will finish this one. It says 2 positive numbers. You have one like this on your homework. 2 positive numbers add up to 18. What is the maximum product of the 2 numbers? 2 positive numbers add up to 18. What is the maximum product of the 2 numbers? Now, I'm guessing some of you might be looking at that and saying, I already know the answer to that. You might. It's 81. it's 81. Two numbers add up to 18, that'd be, 17 and 1 add up to 18, right? If you multiply those, you get 17. 2 and 16 add up to 81. Multiply those, you get 32. That's big. 3 and 15 add up to 18. Multiply those, 45. Well, what happens? You get closer and closer to what? 9 and 9. 9 times 9 is 81, and that turns out to be the answer. You don't need calculus for that. It's kind of a basic factor. It's kind of related to the whole perimeter. For a given perimeter, what shape quadrilateral will give you the max area? No, it is a rectangle. I'm sorry, I meant rectangle. For a given rectangle, for a given perimeter, what shape should it be to maximize the area? Square, 9 by 9. Right? That's a related geometric fact, okay? But I want to use the calculus for this. So step 1 is what? Identify what we're trying to maximize. What are we trying to maximize? Product. So I need to write the equation for product. So right away I'm going to write P equals. P for product. V for volume in the last problem. P for product in this problem. Okay, the max product of two numbers. So what should I do? P equals X Y, whatever, right? So that's what I'm trying to maximize. Step 2, right? That was step 2. Write an equation for what we're trying to maximize. We're trying to maximize the product of two numbers. So P equals X times Y. Okay. Now step 3 is get that in terms of one variable. With some secondary information. What other information do we know? The two numbers add up to 18. So how can I write that? Yeah, X plus Y equals 18, which means that Y is equal to 18 minus X. So now I can substitute that in over here. I get P equals X times 18 minus X, which is 18X minus X squared. And now I'm off and running, right? Now I'm ready to do. See, but the new thing here is getting this set up. And for some reason, people would get all befuddled in this problem and setting this up, right? Because you don't know, well, what do I let it equal? I'm trying to find the max product. What do I write down? That's why it makes such a big deal. You want to find a max product? You got to write a P equals equation for product equals. You want a max volume? You need a V equals equation. You want the max profit? You need a P equals equation, right? Find a max product. P equals what? Well, we're multiplying two numbers. Okay, X times Y. Okay, there you go. And so now you're off and going. Now you find your critical points. Now you have to do your endpoints, stuff like that. What's the littlest that X could be? Talk about endpoints. What's the littlest X could be, right? Our max and min we're doing is the biggest P could be, right? We're trying to find the biggest P could be for our max. But for endpoints, we're talking about the inputs. What's the littlest X could be? Well, it didn't say integers. I probably should have said integers. Positive integers, because it could be 0.1, I suppose, right? If we said integers, let's say it's 1, okay? But if it wasn't, let's say 0. Well, 0 is not really an integer, or it isn't positive, is it? So that makes sense. I should have said positive integers. Okay, so let's say 1. So the littlest X should be is 1. What's the biggest X should be? 17. So those would be your inputs, right? 1 and 17. So if you want to do your list of candidates, stuff like that, because I think you're going to have to, because you're only going to hit one candidate. Now, if you want to ignore endpoints on that case, and you want to do one candidate and do a number line, you could do that too. Okay, your homework is 4.3 day 1, so you can get started on that. So if you get stuck, you can look in the answer book or ask me or whatever. Okay, so 4.3 day 1.